today hidden variable. It's actually the thing that is not hidden, because the person here would see it's +1/2 or -1/2. And the only reason why Wigner doesn't assign now the state +1/2 or Wigner's state assignment here doesn't contradict the fact that there was actually an outcome +1/2. This is just an additional information which is added to the theory. So the theory of Bohmian mechanics consists of these states plus the additional information which tells you what actually happened. And of course I can always say this is the quantum mechanical state, but actually there was this outcome. There's no contradiction to that. And that's what Bohmian mechanics does. It just says there is in addition this information. Just Wigner doesn't know it because he doesn't have access. So, but that doesn't make a difference. Another example is cubism. In cubism, all states are interpreted as states of knowledge about future outcomes. So here one could say the friend has certain knowledge. He has the knowledge of what Z is, and he, for example, knows from that if he measured now the spin again, he would again see the same outcome. I mean, if he has seen +1/2 and measures again, he would again get 1/2. Whereas Wigner, if you look at this state, and if you take the trace over everything except the spin, then it's just a maximally mixed state over the spin. So a Bayesian or a cubist would say, Wigner just assigns a maximally mixed state to the spin, and this just reflects the fact that he has no idea what the spin is. And indeed, if he would apply a measurement now himself, he would equally likely get a +1/2 or -1/2 from his perspective. So it's all consistent. So you see, current interpretations essentially say there's no problem here. And what I'm going to do now is essentially to extend this experiment, at least in such a way that most, or at least many known interpretations, again still run into a contradiction. So this kind of easy way out to say, okay, these are just different states we talk about, different persons, they don't work any longer. And here it somehow works because these people never can communicate, because if Wigner decided to find out what is Z, he would actually have to look into the box and couldn't apply this complicated measurement any longer. He would just apply a measurement in the +1/2, -1/2 basis. But he has to decide what he does. So if he opened the box, he would of course change the state and so on, and so he could no longer apply this measurement. So what I'm going to do is to somehow extend it in such a way that Wigner can find out what the value of Z is without opening the box. That's kind of the main idea. And this seems a priori impossible, because how do you know the value of Z without opening the box? But the trick is to somehow prepare the spin that comes in a particular way.
So are you expecting me to be concerned if two different agents do assign different states?
No.
Okay.
No, yes. So actually that's so what current interpretations say, for example, cubism, is that's perfectly fine. That just reflects the agent's different information. So the contradiction I'm aiming at is kind of a more operational one. I want to say at the end it's a problem if we talk about outcomes. And for example, I mean, okay, just to the punchline of the talk will be, I will, for example, do an analysis and find out if I measure this system here, I will see +1/2. But I also analyze what you would say if you use quantum mechanics and make a prediction, and I find out that with certainty would say it's -1/2. So when I analyze the system directly, I find it's +1/2, but if I analyze how you analyze the system, I come to the conclusion you find -1/2. And that's now a contradiction about the outcomes, and that will be the difference to what Wigner did. So that's what the goal is of this whole thing. So I really want to arrive at the contradiction about what I say about the outcome and what I know what you would say about the outcome. That's what, and there I would then hope you would say this is really more problematic. Whether it's a real problem, that is up to discussion, but it's certainly a different level of a problem than here. Maybe just a last remark before I continue, because we have yesterday heard Jess Riedel's talk about a classical Bayes, and we shouldn't do different measurements. So I think here it's again important to keep in mind that when we talk about states, we always have to fix a time when we talk about the state. So for example, if you talk about the state here, after F has measured in the lab, then I guess, but please correct me if I'm wrong, that according to your criteria of classicality, the value Z would be a classical value, or would correspond to a classical basis. Whereas if I look at this point here, this would be a classical basis. And of course, we are now comparing two different times. That's just a remark. It will be important to actually always write these times, because I'm not talking about a classical basis or something. At one time, we are talking about things that happen at different times. And in some way, you could also see the messages that, of course, a theory can only be predictive if it can talk about correlations between different times, but this turns out to be a problematic thing. Okay, so that was all preparation. Now I will use what I wrote here and just extend it in two stages. So I don't think okay, I can erase that later. Let me just draw two additional elements to this. And one first element is that I will say this spin here was prepared by another agent who is also in an isolated lab. Of course, I can do that, so that's why I had here some space left. There is another lab, which I call, let's say, L bar. And the idea is that within these first 10 minutes, the person in this lab prepares the spin, which is spin particle, which is then sent to the second lab. So this lab is isolated, except for one point in time where this spin is sent out. But otherwise, it's perfectly isolated. So what I will assume is that in this lab, there is a random number generator, and I will say more about that in a minute, which outputs a number, which, let's say it's a coin, heads or tails. And again, there is a person, and I need some label of the person, and I will call her F bar. She has a similar role as F, that's why I call her here F bar. Actually, I called her differently, but at some point I got some advice to call these people differently. But there's still, actually someone complained that I put only women in boxes and no men, but I will not change that for the moment. I hope that's fine for you. So this is not meant to have any other implications. So here, this girl follows a rule. If R is equal to tails, let's start with head, then she kind of does the experiment in the simple case. The simple is the one which is much easier to understand, where phi s, the spin is prepared, let's say, in the spin down state. There's no superposition at the end. This is just the spin down state. But if R is tails, then phi s shall be prepared in the spin right state. So remember, spin right is just up plus down. Okay, so that's something we can do, of course. And let's, in addition, assume, just to be more specific, that this is a quantum random number generator. So assume that there is actually a state here initially, which I prepare as, and it will be a slightly biased one. So heads appears only half as frequently as tails. This will be needed for the argument. Don't worry about that for the moment. I will need that only later. So we think of this as a state that is measured in the space is ht. This is just a way to implement the random number generator. But this is going to be important, that it's biased in that way. Okay, so that was the first addition to the experiment. And this, we can still, there's nothing, let's say, more difficult now happening, but let me nevertheless already write down a statement or two statements which we can make about this experiment. And from now on, I will always take the perspective of these agents. So because I want to, actually, the reason why I'm doing that is that when I presented this to people all said, oh, you just have to use that and that interpretation and then everything resolves. But the safe perspective, which is essentially true in any interpretation, is to say, if I'm always careful in saying who makes a statement, then even people who defend a very subjective view of quantum theory, like cubists, are happy with that. So in some way I want to say that we don't assume a priori that there are some absolute truths. There is only statements that we make, from my perspective. And I don't claim at all that a statement that I make is also a true statement for someone else. But what I'm assuming is that everyone is using quantum theory. So that's the only truth everyone agrees with. So in other words, what I'm assuming here is that all these agents know quantum theory, but they have access to different information. They see different things. For example, F bar sees R, and F sees Z, and so therefore they will make different conclusions because they see different things. But of course they have certain things some common knowledge that will arise, and that will lead to problems. So let me start with the statement that F could make, and I will call that statement SF because it's a statement F could make. And F could make this statement that, let's say, certainly at time, let's say, 0.9, just before this measurement starts, let's say 0.9. So if she has seen tails, then she of course knows by definition that, she has to do that, she has to prepare the spin right. So I'm here not in a cryptographic scenario, no one is cheating, she just does what it's supposed to do. And so she knows then, and now I'm using this careful formulation, she would say then I'm certain that W will know or observe, but I use this word know to be more neutral in that sense because people usually are unhappy with the word observation, but he will observe it, and so it's from his perspective, he will observe fail. That's actually what we said before, because we said that if R is tail, then the spin is prepared as spin right, and if there is spin right, we already calculate or said, this was defined in that way, that W gives with certainty the outcome fail. That is nothing else than the statement I made before, slightly rewritten in these terms of R. So that's a statement I think no one would disagree with, unless you are in a collapse theory. Then, of course, you cannot do that big measurement that Wigner would do. Now there's another statement. This is a statement from the perspective F bar. This was a mistake. So this is because only F bar has access to R. So F cannot make that statement. But let me now also write what F can say. F can also make a statement. Let's, for example, say that she observes plus 1/2, and she has certainly finished this observation at time 19. And then she could say, then I'm certain that F knew, and at time t equal 0.09, that she can say something about R. And now it's always good to make sure that people still are attentive. So who knows what she is certain about? That F bar, yes. Knew, yes, right, thanks. Something about the value R. So what does she know? So does anyone see that immediately? This is. So, yes, it has to be tails. Because if it was heads, the spin would have been down. So with certainty, would not have seen plus 1/2. So if she sees plus 1/2, it must have been tails. Okay, that's a conclusion we would also all agree. This is something we could even do in. There's no measurement involved of agents. We could just do that, and we will always find that F is right with this statement. So there's also nothing to be worried about. So here we have already two statements, and I will need a third one.
So you corrected like this SF to SF bar.
Yes, here, yes, right.
And then you said, well, it's because F cannot know what the outcome of the coin is.
A priori, yes. Maybe she will know it later.
Can't they still make a statement like that
if she, yes, right. Yeah, yes, right. So actually, this statement is someone everyone could make because I have written an if, but I will later use it in a way. Okay, I could. That's right. Thanks for the remark. I could write many more statements that others could make, but I will just write those down that I will need to actually arrive at the contradiction. These are certainly safe ones, and we could say this is something F will at some point know. So it makes sense to write this statement because clearly she will observe it and then she can make this conclusion. But indeed, that's just a statement that is generally true. We make it now, and we just say F could also make it. So now I need to add one final element. So there's still some space left, and this is very similar to what I did here. I just measure this whole lab L bar. So we think of this starting at time 20, there is a huge measurement. I mean, huge by, I mean, you have to measure the whole lab. So this is not a technically feasible measurement, but we are talking here about a thought experiment. Like, I mean, we are used to that. We have thought experiment are people being thrown into black holes. So this is similarly unrealistic, but it's a thought experiment. So I call this outcome W bar, and I will also use a basis which I call OK fail, but this is now, of course, on a different system, on L bar. So I have to define what I mean by that, but before I define it, let me also draw a person here, because I will also assume that this measurement is actually carried out by someone, and I call this person W bar. So what is OK? L bar, so probably you can guess, I do just the same thing I did essentially before. Of course, if this, I mean, depending on what the coin is, the person will know the coin is heads or tails. So I can just say, what is the state of the whole lab if the outcome of the random number generator was heads, and what is the state of the whole lab if it was tails? And I can write these states as, I mean, the same, I will now not go into details because it's analogous to what we did before. So there's a state of the lab which reflects that it was heads and one